Number 7. Okay, got these trees in the forest, and you got these birds in the forest, and you want to see, do the birds go to the trees in proportion to what the trees are? In other words, would 40% of these birds here, 156 birds, would 40% of them go to the Douglas fir? Meaning they really don't have any preference. Versus, that's the null hypothesis. Birds go to trees in proportion of what is available. Or the alternative hypothesis, at least one tree type is incorrect, meaning it's either way higher or lower, or multiple trees could be different. Anyway, so there's that. Let's see, we're going to do a chi-square test. So that's what we would write. We would use a chi-square test on this. And we are going to do random, normal, independent. Now the normal is the fact that we have at least 5 birds on each type of tree, which we do. Even there's 7 in the other type of trees, 79 and 70. There you go. Okay, and let's do the math. So I'm just going to start out this way. This is what we observed. 70 in the Douglas fir, 79 in the ponderosa pine, and in the other type of tree, 7. Now let's figure out how many birds we should expect. So in other words, we would do what? 54% of 156. And the answer is 84.24. How do I do that? I multiply 0.54 times 156. And then I'm going to do, what is the other one? 40% of 156. And that should be in the Douglas fir. No, ponderosa pine. Sorry, 40% were ponderosa pine. So let's do that. 0.4 times 156. And the answer is 62.4. And then 7 in the other types of trees. And what do we do with that? So there's only 6% left. So 0.06 times 156 gives us the number for the other types of trees. And that is 9.36. 9.36. So these are what we expect. This is what we observed. Now, are they far enough off for us to say, yeah, the birds seem to like one type of tree rather than the other? So I'm just going to do this. Stat over to Tess, and I'm going to do GOF, G-O-F, the chi-square goodness of fit test. So all I have to do to start out with is put this into list 1 and this into list 2, then I go to the test. So let me put those into the list first, list 1 and list 2. And I put those into list 1 and list 2. I went over to stat and down to the chi-square goodness of fit test, and it's L1 and L2. In fact, they do the degree of frequency for me, and I calculate, and here are my numbers. Well, the chi-square, if we were to do it by hand, oops, that's not a 0, that's a 2, we would end up with 7.4. Now, the p-value for this situation would be 0.024. Okay, now after we do that, and the p-value is below our alpha level, which we would have at 0.05 in this case, what do? We reject the null hypothesis and say, yes, we have enough evidence here to say that the birds seem to like one tree versus a different tree. Okay, there we go. So why is chi-square not appropriate in this situation? We take 50 students and we look at the average amount of time that they spend on homework. Well, we're not counting anything. If you notice on the problems that we've done or you've tried so far, we're counting things. So we pour out the M&Ms and we count how many blue M&Ms are there. not an average amount. We actually count how many we observe. Observed versus expected. Also, if you think about your own homework habits, the days are not independent. In other words, if you would tend to have a lot of homework probably on Sunday night because you have school on Monday, versus you probably don't do much homework on Saturday and Friday because you're going to save it until Sunday. Those are not independent. These days are having an effect on this day. So, not independent. One has an effect on another day. Okay, so there's that. Okay, Benford's Law. So, they think that, now if you read this, let's see, a company is accused of committing fraud, which means they are not putting down what things actually cost and trying to steal money, basically. So they take 250 invoices. Now they should follow this. One shows up in the front of how much something costs more often than any other number, 30% of the time. And here are the percentages for the other numbers. So they take a look at these 250 invoices, which are down here, and we are going to compare these inverses, the observed, with what we should expect to see. So what we're going to do is we're going to take 250 and multiply it by each one of these percentages. So what I'm going to do is I'm going to put this row of numbers into list 1 and multiply it by 250. And then I'm going to write that down here to see what we should expect to see. So 250 times this number, put it under there. 250 times this number, put it under there. Okay? So let me do that. So here we have it. This is what we observed, these numbers. This is what we should expect. So we're off a little bit. Some of them are close, like this one is close to what we should have expected, but this is double what we should see. So we're going to say, well, how far off are we? That's what we're doing with the chi-squared. So I did get a little ahead of myself here. The null hypothesis is that all of the percentages are correct, and then the alternative hypothesis is that at least one or more of this group of numbers is off, and by how much. So null hypothesis, alternative hypothesis. And let's see, and don't forget that we have to do random, normal, independent, and the normal is the only one that's different for us, and we have 5 in each one of these groups, so we're good to go for that. Okay, so I'm just going to put it in the calculator. And what I do is I put list 1 is this group, and list 2 is this group. So I put them into the calculator, stat, over to tests, and we are going to go to the chi-square goodness of fit test. So that's part of our plan, right? The goodness, the GOF, goodness of fit. Okay, let me do that. List 1, list 2. And don't forget, the degrees of frequency in this case are 1 less than how many categories we have. So degrees of frequency would be 8. Now I put it in the calculator, and it tells me that my chi-square number, chi-square, how far are we off, is 21.56. That seems like a lot to me. Okay, and sometimes it depends on the degrees of frequency, but the p-value, calculator tells me, is 0.0057. Okay, what is our conclusion? Our conclusion is we are going to reject the null hypothesis and say that we have a pretty good idea that this company is committing fraud. Because if it was true that they were in line with Bedford's Law, the fact that their 250 invoices came in this far off, if it was true, would only happen 0.5% of the time. Okay, there we go. So type 1 and type 2 is just like what we've done before. So we're looking at, in this case, a type 1 error is we reject the null hypothesis, but it's a mistake. That's type 1 error. We say that they're committing fraud, but they actually aren't. That could be a little embarrassing. And then the other type is type 2 is if we said, oh, they're following Bedford's Law, so they're fine, they're not cheating us. What's the consequence of that? They continue to steal money from us. So there's that.